Let's see, Jenna, I ran into an email from you a day or two ago saying you couldn't find the class or something like that. I think it was 2 days ago, but apparently you did because you were there 2 days ago, if I remember right.
Yeah, it wasn't showing up in my course catalog type thing where I could
Okay.
favorite it. And then right before class started, it showed up, so I was able to get in.
Okay. Yeah, for some reason there's quite a delay between when students register and when it shows up in their course catalog. So that's just the way it is, I guess.
I was just glad it showed up.
Let's see. I'm in the process of making some big print versions of the example problems that I want to do today here. So let's see. I need to get those made and printed before we can start on what we're doing today. So Control A. That should work. Wow, I wonder what the margin size is on these things. Okay. Okay, let's see. I'm going to switch over to a different screen. This morning, I put up our first homework assignment on the sapling homework stuff, and I put up an announcement for how to register for sapling, and it'll be $32 for the quarter. They'll tell you $32 for the semester, but anyway, hopefully you can get going on that. And this is a real short assignment. Well, relatively short. It's 7 questions, but I don't think you should have any trouble with those if you've been keeping up with the lectures and following along on these things. I also put some assignments on there that are kind of get acquainted with sapling types of things. And if you complete those, they'll actually be extra credit points. So there are about 3 of them. One of them is a math review, and the other one is a bit about how to input answers in sapling and things like that. And they're just ways to familiarize yourself with the process a bit. Of the homework systems that I've used over the years, sapling is one of the easier ones to deal with, believe it or not. Last quarter, I used one in astronomy that was just horrible, and I'm not using it this quarter. It was a headache from the word go, so hopefully we'll get going on this stuff. All right, today we're going to be looking at situations where things accelerate. And yesterday, one of the problems that we did not do was, oh, let's see, let's hope I can find it now, was one where there would have been acceleration. It was on the handout that I had. Here it is. It's this problem here, and just want to, it's another one of those things where we've got the position versus time for an object, and we're going to try to graph it. But on this one, it's maybe a little more challenging because the distance that it's at the 10th second is 145 meters out. And that won't quite fit on here, but I can fudge easy enough to make that work. So again, we're going to graph the position as a function of time. The position is before as a function of, so it goes on the vertical axis, and that'll be x, and our units will be meters. And then time goes after as a function of, and so time goes on the horizontal axis, and that'll be in seconds. And I'll just quickly graph these things in here. Let's see, for the seconds, I'm just going to go 0 down here, 5 here, and 10 here, and those work pretty good. For the position, I'm going to go, well, 0 here, but let each one of these be 10. And I looked at this ahead of time, is how I figured it out so fast. So this will be 50 here. This will be 100 here. And I don't know if you can see or not, but these lines are heavier a little bit. If you actually printed it off, you might be able to see that. And this top line is going to be 130. I need to go to 145, but I can fudge on that last data point and make it work. So the first starts off at 5 meters at time 0. And then it's at 10 meters at 1 second, 17 meters, whoops, excuse me, I screwed up on those. These are each 10. So here's where it starts at 0. 10 meters would be here. 17 meters would be most of the way up to 20. 26 is going to be up here. 37, 1, 2, 3, 7 is going to be about there. It's hard to tell that it's not linear so far, but this is a bigger jump. 50 there, 65, 82, 101, 122, and then let's see, there's 30, 40, 50. So the 145 is going to be about there. And if we look at this thing, kind of connect the dots, which isn't quite legitimate, but I can sort of do it. We see we've got a curve on this one. So that means the slope is changing, and we need to know how to deal with that. So determine the average velocity for the interval 0 seconds to 5 seconds. Okay, the average for that, and I'm using my formula for calculating velocity, which is x2 minus x1 over t2 minus t1, or in this case, it's going to be x of 5 seconds minus x of 0 seconds divided by 5 seconds minus 0 seconds. And so at 5 seconds, it's at 50 meters. At 0 seconds, it was at 5 meters. And 5 seconds minus 0 seconds is 5 seconds. So let's see, that looks like 45 divided by 5 is 9 meters per second. Okay. Then determine the average velocity from 3 seconds to 10 seconds. Well, same thing. V average is going to be the x of 10 seconds minus the x of 3 seconds divided by 10 seconds minus 3 seconds. Okay. And this notation, x is a function of t, so I'm thinking of x of t. And in math class, you would have dealt with functions, I hope, at some point where you'd write it using that kind of notation. And that's what I'm using here. So at 10 seconds, we're at 145 meters. At 3 seconds, we were at 26 meters. And then we've got 10 seconds minus 3 seconds down here. And I'm going to do this on my calculator. I get 17 meters per second. Okay, how do they compare? Well, this one's bigger than that one. In fact, it's almost, that's an equal sign. It's almost twice as much. Can I tell that by looking at the graph? Well, I can if I draw a line, a couple of lines on the graph. And what I'm going to do is draw lines that connect 0 seconds where it is at 0 seconds and where it is at 5 seconds. And the slope of that line is actually the average velocity between those 2 points. And I can get a sense for what that is. Then I do the same thing for 3 seconds and 10 seconds. 1, 2, 3. Here's where it is at 3 seconds, and it's way up there at 10 seconds. And so I draw another line there, and this slope of this line is the average velocity from 3 seconds to 10 seconds. Whoops, I missed the point, but you get the idea. Anyway, this line is steeper than that line. And that means the velocity is changing. When that's happening, we say that the object is accelerating. And the way that we write that, acceleration, in this case, it's a speeding up, but in physics, acceleration is any time you speed up or slow down, or something that we haven't talked about yet because it's in two-dimensional motion. Anytime you change direction, you also accelerate. So acceleration, the definition of it is, and here's a verbal definition first, the rate of change of velocity. Now, I haven't formally defined velocity yet, but velocity is this. We've had an equation for it. Velocity is the rate of change of position. We'll have quite a few times in this class when we talk about the rate of change of things. When we study energy, we'll talk about the rate of change of energy, or when we talk about power, we'll talk about the rate of change of energy, or the rate at which work is done. Anytime we're talking about the rate of something, we end up dividing by delta t at some point. And so this, for velocity, v, we've been doing delta x, that's the change of position, divided by delta t. And so this is the rate of change of position. For acceleration, what we'll have is delta v over delta t. And so that'll be the change in velocity. And so it'll be some V2 minus V1 over T2 minus T1 and so forth. Just like this was X2 minus X1 over T2 minus T1. So acceleration is defined that way. We can have positive acceleration. If V2 is bigger than V1, then that numerator is positive. We always let the time run forward, so the denominator is always going to be positive. But if this is positive, then we have a positive acceleration. If V2 is less than V1, then that numerator is going to be negative, and we'd have a negative acceleration. Now, in everyday language, people will use the term deceleration for a negative acceleration, but we'll just say it's an acceleration with a negative sign, or it's an acceleration in the negative direction. Acceleration has a direction just like velocity does. A velocity going to the right is different from a velocity going to the left, and acceleration going to the right is different from an acceleration going to the left. So we'll be thinking about all of those things as we're doing problems on this stuff. So that's a basic definition of acceleration. Now, something we found out was that if we had a position versus time graph where we had X on the vertical axis and T on the horizontal axis, if we had points that were connected along a nice straight line like this, let's see, I better use a ruler to connect those dots because it's going a little bit weird. Anyway, if that's the case, we'd have a constant velocity. And you've learned back in algebra class when you have a delta y over delta x, that would be the slope of a line. If that slope happens to be constant, then you have a constant velocity. Okay. Well, look at what the acceleration is. It's delta v over delta t. It's got the same kind of relationship that the velocity has, except this isn't going to show up on a position versus time graph that way. In fact, here's a position versus time graph for something that's accelerating, and it ends up being a parabola, is what that happens to be if it's constant acceleration. By the way, the most complicated situation we'll deal with in this class is having constant acceleration. And one possible constant acceleration is 0, which means you have constant velocity. But we won't go any more complicated than that. And that's complicated enough, believe me. So anyway, but this is the same kind of relation, but it would show up on a velocity versus time graph. So if you have constant acceleration, you'll end up with a straight line on a velocity versus time graph. So this would be a constant positive acceleration. You could also have a constant negative acceleration. You could have one that looks like this, and these are all going to be velocity versus time graphs. You could have something that its velocity as a function of time looks like that. That would be a negative acceleration. You could have something, this time I'll have a negative part of the velocity here. So here's velocity on the vertical axis and time on the horizontal axis. You could have the velocity look like that. That's a nice straight line. That means it has a constant acceleration. In this case, the slope of that line is 0. That means it's not accelerating. It's moving with constant speed. And so, but still, that's a constant acceleration situation. Another constant acceleration situation might be one that looked like this. Okay. That's a negative velocity. Okay, but it's flat. It's a nice straight line, no slope to it. And so this would be a constant negative velocity, which means it's moving in the negative x direction. So these are all, this, and that are all constant velocity or constant acceleration situations. The last two happen to be constant velocity as well, because the acceleration is 0, the slope is 0. So what are the equations going to look like for constant acceleration? Well, there's actually a box for them on that formula sheet we were working from yesterday. If I can find where I put it. Here it is. They're all in this little area right here. There are a couple of equations that look like what we were doing yesterday, but they have something special in them. And one of them is x is equal to x naught plus v average times t. Yesterday we were using this equation, and that's one that happens to be true. And then another one that's true for constant acceleration is that v average is going to equal something v naught plus v over 2. Whoops, should have had a 2 there. Not, I was tempted to write something else. Anyway, that's supposed to be a 2. This would be the average velocity between some initial velocity, what it is at time 0, and what it is at some later time. And you just average those things, divide them by 2. So that's one. We won't use these two very often, but once in a while they'll be kind of handy. Another constant acceleration equation, though, and this is one that will make sense if I draw us another picture here. Whoops, that one's been used. I'll draw another graph, and this will be one that's similar to one that we had, but this will be a v versus t graph. And I'm just going to draw a straight line on here, but it's going to have a slope. And so there's a v versus t graph. This is the origin down here. This thing right here is the value of the velocity when the time is equal to 0. That's what we call v naught. And on this graph, it's the vertical intercept. The slope of this graph is equal to a. And if you remember from algebra, when you had a y equals mx plus b, or for the way we always write them, we think of b plus mx. B was the vertical intercept, or called the y-intercept in algebra. Well, instead of b, we've got v naught. The slope of our line is a, and we don't have x. We have t instead. The other equation, or another one that we can get out of here, is that v is equal to v naught, what it is at time 0, plus at. And this is the slope of that. Okay, so this is the line v equals v naught plus at. When t is 0, that thing vanishes and you get v equals v naught. But this lets you figure out the velocity at any future time using that equation. If you know v naught and you know a, you can figure out what the velocity will be at any value of the time. So at least any value for which this is a slope. It may be after a while the car runs out of gas or stops accelerating or something like that. But all right, so those three equations aren't too bad. We're going to use these today some. Now, the tricky equation is getting x as a function of t, and we just graphed that one wherever I put it. Yeah, we graphed this one that ends up looking like a curve. It's actually a parabola. And that equation, I'm not going to bother going through the development of it, although we actually could. It would be a matter of algebra, but it's more than I want to do algebraically here. But it looks like this. X will equal x naught. Whoops, that was supposed to be an x naught. It is that. Plus v naught t. Now, this looks just like the things that we were dealing with yesterday. We solved some problems using that equation yesterday, and that would be the equation of a straight line. But this isn't a straight line. It ends up being a parabola. We have another term that we add on to it, and it's this. 1/2 AT squared. Okay, now things are a little bit more complicated. We've got, this is actually the equation of a parabola, and if you graph that and you know the value of a and v naught and x naught, you could see how it would come out as a parabola. But in fact, I used this equation to figure out the data for this particular graph, and monkeyed around with it that way. So anyway, that's the equation for position as a function of time. And those are most of the constant acceleration equations that we'll deal with. But there's one other one, and this is a handy one sometimes. You can eliminate t from these two equations. And the way you do it is to solve this equation for t. You'd subtract both sides, or v naught from both sides, and then divide both sides by a, and you get v minus v naught over a is equal to t. Then you take that and plug it in to replace t in here. Don't worry about doing it. Unless you like algebra, you can go ahead and do it. And what you do is you get this equation, and I want to make sure I use the same form the book does. You get a, let's see, fifth equation here. V squared is going to equal v naught squared plus 2 times a times, do they write it as delta x or x minus x naught? X minus x naught. Okay, so that's an equation that doesn't even have the time in it. And sometimes this is useful. This is worth knowing. You can usually solve problems without using this, but it means you have to solve one of these two for t first, and then plug it into the other one to figure out the other stuff. So this is one that is kind of nice once in a while. Okay, let's see how to use these things. This is getting more complicated, but it's sort of the next step in complications here. We'll try to start off with simpler situations and then gradually work our way to the more difficult ones. You may not be able to see those equations now. I think if I slide those over, yeah, they're still visible. Then we'll see how these work. We have a car, starts from rest, and after 9.35 seconds is traveling at 27.3 meters per second. Okay, starts from rest, right? That's code. It means v naught is equal to 0. Okay, and the question is, what is its acceleration? Well, we're asking, what is a? Have to go back for the definition of acceleration. It is v2 minus v1 over t2 minus t1, or You can think of it as just the velocity at some later time minus the initial velocity divided by the time when it's at that final velocity. And that's the version that we can use here. At some point, it's going 27.3 meters per second. So that would be the V. Since it started from rest, V naught is 0, so I can just put as -0 there. And the time that it took to get from being at rest to going that fast was 9.35 seconds. So let's see, 27.3 meters per second is about 60 miles an hour. And it's not exactly, but it's kind of close to that. So this is a car that goes from 0 to 60 in 9.35 seconds. If you pay attention to advertisements, a lot of times car manufacturers will brag about how fast a car goes from 0 to 60, which you don't ever want to do starting from a stoplight, because it attracts the attention of those people who have those cars with the nice flashing red and blue lights. So you don't want to tromp on the gas too much at a stoplight when you start up from rest. But anyway, 9.35 seconds isn't a super fast acceleration, but we can calculate it. Just 27.3 meters per second. And I'm going to show you something about the units on here. Now in this problem, I've got 3 significant figures on top and 3 on the bottom, so I can keep 3 for the problem. And I get 2.92. Now on top, I've got meters per second, and on the bottom, I've got seconds. And so we could say that that's meters per second per second. And if you keep it thought of that way, you'll kind of realize that every second that goes by, the speed will increase by 2.92 meters per second. And in much of the world, particularly in Britain, that's the way that they would express that. They'd say meters per second per second. But for some reason in the United States, we don't do it that way. And I'll show you what we do. We think of the units, we'll have meters per second on top of a fraction. And on the bottom, we've got seconds. And that one that's on the bottom, we'll just imagine that it's over a 1. Because if you divide something by 1, you don't change it any. And then we think, okay, fraction on top, fraction on the bottom. You invert the bottom and multiply. And so that changes the units into meters per second times 1 over seconds. Multiplying anything by 1 doesn't change it. Multiplying a second times a second gives you seconds squared. And so that's what the units end up being. And in the United States, for whatever reason, we've gotten in the habit of writing this combination of units as meters per second squared. Okay. It is easier to write it that way, but if you think of it as meters per second, it's a little easier to look at this and think, okay, every second that goes by, the speed increases by 2.92 meters per second. And so that's just what we happen to do. So there's an example of calculating an acceleration. Then, after a little bit of time, the car is traveling at 28.5 meters per second, which is a little more than 60 miles an hour, and it has to stop for a red light. And it takes 8.62 seconds to stop. What is its acceleration? Well, again, acceleration is going to be v2 minus v1 over t2 minus t1, or you can think of it as v final minus v initial over t final minus t initial. Okay. In this case, v initial is the 28.5 meters per second. That's how fast it was going at the start of this interval when it's beginning to stop for the red light. And V final is 0 because it stops. Okay, so I put in a 0 for V final minus the 28.5 meters per second there. And the T final minus T initial, that's how long it takes to stop. So that's the 8.62 seconds. And what do I get? I've got 0 minus 28.5 in the top, which is minus 28.5 divided by 8.62. And I get minus 3.31. And that would either be meters per second or meters per second squared. Okay. And the negative sign tells me that the acceleration is, the velocity is positive. It's going in the positive direction. The negative sign tells me that the acceleration is opposite the motion. And when that's the case, the object will be slowing down. So anytime the velocity is one direction and the acceleration is opposite that, the object is going to be slowing down. If the acceleration and the velocity are in the same direction, it'll be speeding up. If they're opposite, it's slowing down. And that's what that tells me. So those are both fairly large accelerations to be experiencing in a car. Most of the time you accelerate more sedately, I guess you might say. And so you don't do something like that. I've had cars that I don't think could even accelerate from 0 to 60 in 9.35 seconds. When I moved to Moses Lake 28 years ago, I had a 1974 Plymouth Valiant, which had a large engine in it, but it was not functioning well when I got here. And it would take a while to get up to 60 miles an hour. I know that. Kind of a primitive car. Anyway, any questions on those two problems? Those are our first two dealing with acceleration. And so far, all we've been using is just the definition of acceleration to solve those things. Okay, well, let's try another one. My guess is soon we're going to use one of the other equations, but we'll see. A well-thrown ball is caught in a well-padded mitt. All right. If the deceleration of the ball is 2.10 times 10 to the 4th meters per second squared, ooh, we may not have used scientific notation yet. That's something that in the mathematics review on the Sapling website, I think they address a little bit, but I'll just do a quick review for you on that. That 2.10 times 10 to the 4th, and I'm ignoring the units just for a little bit. 10 to the 4th means 10,000. It means a 1 followed by 4 zeros. Okay, so you can think of that as 2.10 times 10,000. Okay, well, if you multiply 2.10 times 10,000, what you get is 21,000. And so this is actually quite a large acceleration, but it's not unusual for something like a thrown baseball. But that's the 10 to the 4th would be 10 times 10 times 10 times 10, which is 10,000. This is just a shorthand notation. And in my other class, especially now, we're dealing with things like electrons and protons and stuff like that, and their masses and their charge. And we pretty much have to use scientific notation, which is what this is called, because if we talk about the mass of a proton, you don't know what mass is yet, but it's 1.67 times 10 to the minus 27th kilograms. Kilogram is the metric system unit of mass. And that's a horrible number. I would never want to write that down in standard notation. You'd start with a 0 and have a string of a whole bunch of zeros before you get to the 167 part. And so we'd be crazy to use standard notation when we're studying things like this. Now, it's a toss-up on something like this, but it's just a nice way of writing it. One nice thing about scientific notation is you can look at this number and instantly know the number of significant figures. It's the start counting here and go to the last 0 that I've got here, and it's 1, 2, 3 significant figures. So that's a nice thing about it. Whereas if I write it as 21,000 meters per second, I don't know how many significant figures there are looking at that number. There are at least 2, both the 2 and the 1 are significant, but I don't know if any of these zeros are significant when it's only written that way. So that's why we wrote it that way. Okay, let's go and solve this problem now. Anyway, a well-thrown ball is caught in a well-padded mitt. If the deceleration of the ball is 2.10 times 10 to the 4th, notice they said deceleration. That's a negative acceleration. And 1.85 milliseconds, a millisecond is 10 to the minus 3rd seconds, elapses from the time the ball first touches the mitt until it stops. What was the initial velocity of the ball? Holy cow. Let's see what we can do here. Well, this is still using the definition of acceleration, which is acceleration equals v final minus v initial over t final minus t initial. Okay, they told me what the delta t was down here. It's 1.85 milliseconds. They told me, actually, I don't know either one of these velocities except the ball is caught. That sounds, and then the ball stops. All right, so v final is 0. What I don't know is v initial. T final minus t initial is how long it takes to stop the ball. That's the time from when the ball first touches the mitt, when it's going at its v initial, until it stops. That's 1.85 milliseconds. So this is 1.85, and they say a millisecond is 10 to the minus 3rd seconds. So I can replace the ms here with times 10 to the minus 3rd. So, and then since I used up it also needs a second at the end of it. So that's how long the time interval is in scientific notation. And what do we know? Oh, we know the acceleration. It's a deceleration. It's that magnitude, but a deceleration is negative. And so I can say A is negative 2.10 times 10 to the 4th meters per second squared. And A is equal to V final, which is 0, minus V initial, which I don't know, divided by that time interval, 1.85 times 10 to the minus 3rd seconds. Okay, well, that numerator just changes into 0 minus V initial is just minus V initial. And I've still got that on the bottom there. So let's just multiply both sides by that. When I do that, I tend to think of, I'll just multiply out from under by 1.85 times 10 to the minus third seconds. And so I just do that. And over here on the left side, I'll then have minus 2.10 times 10 to the fourth meters per second squared times 1.85 times 10 to the minus third seconds, and that'll equal minus V initial. And when I multiply those two together, I get a negative number. And I'll show you how I do it on my calculator. I've got mine in scientific notation all the time. And I don't know if you've noticed that when it's in that, it gives me this E0 notation. Your calculation may express those differently, but that's what mine does. But to put it into there, for this negative number here, first I hit a minus sign there and 2.10. And on this particular model of calculator, I just hit the EE button and then it's got a 4 on it. And that number's in. That's all I have to do. I don't have to put in a times 10 to the or anything. And then I want to multiply it by this number, which is 1.85 EE3. And that's all I do for putting those numbers in. It's pretty easy. And you have this function built into your calculator if you've got a TI-80 or a TI-84, except that on those models, you have to hit another button before you hit the EE. You have to hit the second EE. It's just because of the nature of those things. Anyway, I just have to multiply those. And I get, whoops, I forgot to put a negative exponent on that time. So I'll go back and fix that. Let's see, delete minus 3. There we go. Yeah, I came up with a speed that was faster than this, almost the speed of light for this baseball, this well-thrown ball, and that's not reasonable. So anyway, I get minus 3.89, or no, minus 38.9. It's in scientific notation. Meters per second, because when I multiply meters per second squared times seconds, this second divides with one of those, leaving one down there, and so I'll have meters per second. And notice again, I kept track of my units everywhere in the calculation. Now that's minus V initial. If you imagine multiplying both sides by -1, turns both of them positive, so V initial is equal to 38.9 meters per second. So they called that a well-thrown ball. Let's do an example unit change problem here just to see how this comes out. And this is where we'll stop for today. The initial, 38.9 meters per second. And I want to convert this to miles per hour. Okay, one thing that I need to know is that 1 mile is equal to 1,609 meters. And so one of the funny looking ones I'm going to multiply by is going to take advantage of that. Now, this thing has meters on top, so I'll make my funny looking one have meters on the bottom, and it's going to look like this. 1 mile over 1,609 meters. Okay, these two things are equal. When you divide a number by its equal, you get 1. And so I did that. And you can see that the meters will go away in that case. Then I want to use another funny looking one. 1 hour is 3,600 seconds. Here the seconds are on the bottom, so I'm going to want them on the top. So I'll multiply by 3,600 seconds divided by 1 hour. And the seconds will go away. And the units that are left are miles on top and hours on the bottom. And let's see how many we get. Let's see, that was 38.9. And I get about 86.9 miles per hour. Okay, well, that's a, nowadays people are throwing fastballs well over 90 miles an hour, some of them over 100 miles an hour, but it's still a relatively fast baseball. Those are the professionals that are doing that. That's pretty fast. So 38.9 meters per second. Now, all three of the problems that we did today, we used just the definition of acceleration for figuring those things out. And we haven't used any of the equations of motion that I wrote down here for solving those problems yet. So Monday, we'll do some with those. And I think for the homework assignment, which is due Monday night at 11:59 p.m., maybe the last one or two, we might have to use one of these equations for. But the rest of them you should be able to do just with what we were doing yesterday and that definition of acceleration. Okay, I'm also going to be, for the lab this week, I want you to be thinking about unit conversion and significant figures. And I'm actually going to put up a quiz on significant figures and a practice sheet for unit conversion. And so I'll be putting those up this afternoon. The quiz, you're going to have a week to do it, so it won't, shouldn't strap you for time. If you're good at significant figures already, you could finish that quiz in 5 minutes. Otherwise, I want you to let's see. I want you to watch the videos on significant figures, and I'll put links to those up there somewhere. Okay. Any questions?
Yeah, so when I did the last equation and I typed it into my calculator, my answer was 87.0. Would I get points taken off, or how would I be able to do the equation correctly to get 86.9?
Let's see, what you might have done was just take one of these numbers that had been rounded off in order to get that. It was probably this one, actually. Yeah, I bet that's what you did. Because the way that I got the 0.9 on there was to round up 0.85 to 0.9. And you probably left 0.85 in your calculator, I think. Although I can't tell really from here. But no, you wouldn't get marked wrong for that, because 87.0 is not that different from 86.9. And when you write a number in this way, it's understood that the uncertainty is in the last digit. And so a little, 87.0 is only 1/10 of a thing different from that. And if you'd written 87 or 86.8, that would still be close enough. So I'm not going to worry about that. And I think on sapling, if you're within 2% of the correct number, which is a lot more than that, then the difference that you were talking about, they still count it as correct. So you'd be okay.
Okay, thank you.
Okay, well, have nice weekends.
Wait, one more thing. Is there a lab this week?
The lab for this week is just taking that quiz on significant figures, which I haven't posted yet. And
Okay.
practicing with unit conversions. So.
All right. So it's not like an official assignment necessarily, just doing
No.
the stuff. Okay.
Yeah. All righty. Well, have a good weekend. And I guess it says I'm still screen sharing. I'll stop the share. There we go. That's why it was so odd. And see you Monday.